Okay, great, Michael. I guess it's time, so we get going now.
Absolutely. You go ahead, Tajinda.
Okay, great. Good evening, good morning, everyone. So it's a great pleasure to welcome Professor Andrew Hamilton to give the 15th OSMU lecture today on string theory, unification, and geometric algebra. Andrew is a faculty at the University of Colorado in Boulder. He obtained his BA in mathematics from St. Catherine's College at Oxford and his PhD in astronomy from University of Virginia in Charlottesville. And I'm very impressed and full of admiration that Andrew has such very wide-ranging research interests in general relativity, gravitation, cosmology, black hole physics, unification, geometric algebra, and as he mentioned just now, string theory as well. And so very happy to hand over to you, Andrew. Please take over.
Thank you very much, Tajenda and Michael, for the invite. And thank you to everyone who's coming and listening to today. I'm going to be talking about string theory, unification, and geometric algebra. String theory is, in my opinion, the most promising theory of quantum gravity out there. That's why I'm interested in it. But string theory seems to have been spinning its wheels for at least a decade or two. And I'm going to advocate the way that we can maybe open the dam is by getting rid of supersymmetry altogether. I mean, not just allowing supersymmetry to be broken, but getting rid of supersymmetry and going back to the old-fashioned bosonic string theory that was popular in the 1970s, or at least thought about in the 1970s. Supersymmetry, what is it? It's an unobserved hypothesized symmetry whose generators are fermionic as opposed to bosonic. And the observed symmetries of nature are those of gauge theories and of general relativity, and those symmetries are all bosonic. Now, a quarter century ago, superstring theory was poised to be the theory of everything. And it made predictions. And the key prediction that it was making is that we physicists would see supersymmetric partners of the particles that we know about at the Large Hadron Collider, not far above the TeV scale. The Large Hadron Collider ran at 8 TeV when it started, and then upgraded to 13 TeV in 2015. And the Higgs boson was discovered at the Large Hadron Collider in 2012. But superpartners have remained stubbornly missing. Now, it is held that supersymmetry is essential to string theory. And I want to remind you what those arguments are. And I'm going to point out that, in my opinion, those arguments are not robust. They are not mathematically robust. The first argument is that it's only supersymmetric string theories that admit fermions. The alternative to supersymmetric string theories is bosonic string theories. And the claim in string theory is that bosonic string theories do not admit fermions. The second argument was that the ground state of bosonic string theories is tachyonic, which means it's negative mass squared and therefore unstable. And if you look around at the vacuum today, you can see that the vacuum seems to be stable. It's not going away. And there were other arguments in favor of supersymmetry. One of them was that scalar particles like the Higgs scalar have quadratic divergences which tend to pull their masses up. But there's a cancellation, if there is supersymmetry, between bosons and fermions that makes that divergence go away. But that requires that supersymmetry occurs not far above the mass of the electron-Higgs boson at 125 GeV. And of course, that is precisely the thing that has not been seen. So plainly, there's something missing in that argument. It seems not to be working. And then finally, there's a historical reason, which is that supersymmetry was pivotal to the first superstring revolution of 1984, and it has continued to play an absolutely pivotal role in subsequent events, including, for example, the second superstring revolution and then ADS-CFT. So I'm going to argue that, yes, bosonic string theories do admit fermions. Where does this myth come from? The myth that only supersymmetric string theories admit fermions. This came home to me on the second report of two anonymous referees to a paper that I submitted at the beginning of this year on bosonic string theory, putting fermions at the end of open bosonic strings. And both referees said, no, you cannot put fermions at the end of bosonic strings. And in my reply to the first rejection, I said, look at the mathematics. What you say is false, what I say is correct. And both of them said, no, that's not true. Well, what the referees said was simply wrong. It is a fact of nature that whenever fermions pair up, their center of mass motion is bosonic. And there's plenty of experimental evidence for that. One example, for example, is Cooper pairs of electrons in a superconductor. Cooper pairs can form pairs, and they are fermions. The electrons are fermions, but you can have two sets of pairs, for example, like this and that, and their center of mass motion is bosonic, so that pairs of pairs can go in lockstep, and they produce superconductivity. The same phenomenon happens in fermionic superfluids and in fermionic condensates. On the right-hand side, you can see the first fermionic condensate produced in Debbie Jin's lab in my institution, Gilla, back in 2003. So I see a raised hand. Should I pause or?
Can I ask a quick question? On this point, would you consider a pion in QCD, which is understood as a bound state of antiparallel quarks, spin antiparallel quarks, therefore spin zero, as another example in this list? Would that be a valid example in your list?
Yes, it is, but I'll talk more about that in just a little while. In fact, I'll talk about it in the next slide. The next slide is where does this myth that bosonic strings cannot have fermionic endpoints come from? And after getting the rejection, I went through the literature and the textbooks rather thoroughly, and I think I can trace it back to the canonical textbook on superstring theory by Green, Schwartz, and Witten back in 1987. Their first chapter is a beautiful exposition of the historical origins of string theory, and it's precisely that a meson is a bound state of a quark at one end and an antiquark on the other, and there is a string that is some sort of a force that holds the quark and the antiquark together. And then Green, Schwartz, and Witten say in this chapter one, of course, the model has a few problems. First, there are tachyons, and what is more, the model is regrettably lacking in baryons or fermions of any kind. This is, and then they expand on this idea in chapter 6 after going through open strings. This is their figure 6.1, an open string with a quark n at one end and an antiquark n bar at the other, transforming under the symmetry group. And the symmetry group that they were considering was that of SU3, the color group. But there's a footnote at the bottom of the page, but it says, by quarks and antiquarks, notice the quotes here, we only mean labels representing certain quantum numbers. To attach mass or spin at the ends of open strings would ruin the analysis described in the previous chapter. And you can detect a sort of a tension between the mathematics, which I'm sure they understand very well, and the conceptual picture of what this string is doing. Mathematically, a RB bar gluon is in fact mathematically an outer product of an R quark and a B antiquark. So mathematically, there's no question about how these things transform. Green, Schwarz, and Witten knew that n transformed in the spinor representation of SU3, and they knew that the n bar transformed in the conjugate spinor representation of N3, and that they knew that the string itself transformed in the n bar representation, the adjoint of SU3, which of course is exactly how the standard model of the color force works. There is something that Green, Schwarz, and Witten did not know about at that time, which was D-branes. D-branes were invented or discovered by Joe Polchinski in 1995. D-branes are defined as being surfaces upon which open strings can terminate. Here's an open string, and it's oscillating up and down, and its ends are attached to a D-brane. And massless gauge bosons, when you quantize the open string, are eigenstates at the first excited level. They're transverse. They oscillate up and down. And the fermions on the D-brane, they carry charge and they have spin 1, and the fermions of the D-brane are not excited. Notice that the D-brane is not moving here. The fermions are in the ground state. There are, however, the fermions can live on the D-brane, and the transverse oscillations of the D-brane correspond to longitudinal oscillations of the string. So the gauge boson itself is not excited there. Okay, the fermion is not in the ground state, but the boson is in the ground state. And again, that's exactly how the standard model of the color force works. Exactly how the string and the fermion can interact in this case was pointed out by Marcus and Sagnotti before the advent of D-branes. They pointed out that if you add to the two-dimensional string action a one-dimensional boundary term, a Dirac term of massless fermions, the endpoint, then the Dirac boundary term leaves the propagation of the free bosonic string unchanged, but introduces bosonic gauge factors to the interaction of the fermions on the D-brane. Again, that is exactly like the behavior of the color force in the standard model. Bottom line, yes, a bosonic theory does admit fermions, and those fermions must sit on a D-brane. What about the second objection, that the ground state of the bosonic string is tachyonic? That is true. It is tachyonic. What is the tachyon? Well, it's the string. It's not a nothing thing. It's a string, but it's this string in the eigenstate of no oscillation at all. Here it is. It's not oscillating. Its endpoints are not oscillating. Nothing is happening here. That's the ground state. That's the vacuum. But as Marcus and Sagnotti pointed out in their same paper back in 1987, the endpoints of the tachyonic string attached to the D-brane, just the same as the excited gauge bosons. And they interact, the tachyon interacts with the fermions of the D-brane with the same gauge group as the massless gauge bosons at the first excited level. And those properties of the tachyon are precisely those of a Higgs boson. Remember that a Higgs boson is a multiplet of the symmetry that the Higgs boson then breaks. And the vacuum state of the Higgs field, where it is all components of the multiplet are vanishing, identically vanishing. Here is the vacuum Higgs state sitting at the top of a quartic potential. It's tachyonically unstable, so it tends to fall down to the true vacuum state displaced off to some finite point. And of course, the tachyon has spin 0, and the Higgs boson has spin 0. Now, the D-branes that Polchinski originally introduced in 1995 that he emphasized were so-called stable BPS D-branes. For example, in type 2a string theory, the stable D-branes have even dimensions, but there are also unstable D-branes which have complementary odd dimension, again in type 2a. And so the D-brane is unstable. Okay, so it isn't actually the D-brane itself that is unstable. It's the holistic system of the string and the D-brane to which it is attached that it is unstable. Well, the idea that the tachyon might have some Higgs-like behavior was, of course, that was explored by string theorists at the end of the 1990s. Ashoki Sen was the first one to do so. And he proposed that the unstable D-brane would decay to a stable D-brane of one fewer dimension. And that definitely seemed to make some sense. And the mathematics seemed to work out, at least to some extent. There were some consistency tests. But if you want to connect the tachyon to, quotes, the reality that we know of, which is the Higgs field as something that breaks symmetries, then Higgs theory suggests a different outcome, which is tachyon decay is associated not with the decay of a D-brane, but rather with a breaking of the symmetry group. And that breaking of the symmetry group reduces the holonomy group of the D-brane. And I'll remind you that the holonomy group of a manifold is the group of transformations of the tangent space. There's the tangent space. Here's my manifold. Parallel transporting it comes back around a closed loop to where it started. Then that tangent space is rotated a bit. And in the case, for example, of a Riemannian manifold, that holonomy group is SON, the special orthogonal group in n dimensions. And in general, the holonomy group can be a subgroup of that group. Fine. I hope I planted it in your brain, the idea that maybe supersymmetry is something that you should think about getting rid of altogether, not just breaking it, but get rid of it altogether. Without supersymmetry, a bosonic string theory can be constructed that actually resembles reality. It looks very much like the theory of the strong force considered in the 1970s, but the gauge group is that of a grand unified theory, not just of the strong force. It's a bosonic open string theory, and bosonic open strings must live in 26 dimensions. And yes, the ground state is tachyonic. But as I have argued, the tachyonic ground state is nothing more than a Higgs multiplet transforming in the adjoint representation, the same as the gauge group. And the fermions live on a D-brane, which is some subspace of that 26-dimensional thing. And as I've just argued, symmetry breaking is a reduction of the gauge group, and the holonomy group of the D-brane is a subgroup of the gauge group. So at this point, I could even stop lecturing altogether and say, go home and figure out your favorite string theory, maybe using octonions, whatever you like. My favorite is spin 10, and I'll continue to talk about that. 1, 2, 3, 4, 5. Spin 10. Spin 10 is the grandfather of grand unified groups that were discovered in the mid-1970s following the standard model becoming very successful in 1974 or so. Spin 10 elegantly contains the three forces of the standard model: hypercharge, weak isospin, and the color groups U1 cross SU2 cross SU3. Spin 10, there were two other grand unified groups, SU5 and the Patti-Salam group, spin 4 cross spin 6. And both of those other groups are subgroups of spin 10. So spin 10, in some sense, is the father or mother, if you prefer, of them all. One of the advantages of spin 10 is that it contains all of the spinners of a generation of the standard model in a single multiplet. Now, as Wilczek emphasized in 1998, in any spin n group, the spinners are indexed by a bit code with n over 2 bits. So in spin 10, there's 5 bits, and they consist of 2 weak bits, which I call Y and Z, and 3 color bits, which I call R, G, and B. And it's a bit code, so there are 2 to the 5 or 32 spinners. I've got this lovely model here of the standard model of physics, all the fermions of the standard model of physics. There they are. I've got 5 bits. There's a Y bit, a Z bit, an R bit, a G bit and a green bit. The YZ are weak bits and the RGB are the color bits. This is a right-handed neutrino. If I flip the Y bit, it becomes a left-handed neutrino. If I then flip the Z bit, it becomes an electron, and I can see this is a right-handed electron. If I flip the Y bit back up again, it becomes a left-handed electron. And if instead of having all three color bits up, I have just one up, say the red bit, then this is a red quark. And I can see that the Z bit is down, so this is a down quark, and the Y and the Z bits are anti-aligned, so it's left-handed. If I flip the Z bit to up, it's now an up quark, and this is a right-handed one. Again, if I flip the Y bit, it becomes a left-handed red quark. Isn't that beautiful? That is absolutely lovely. That should be taught at nursery school or something like that. But there's something missing there. And that missing thing is the Lorentz group. In the standard picture of this 5-bit spin 10 thing, each of these spinners is itself a Weil spinner. Now, I'm going to argue that it's obvious that the simplest extension of spin 10 to include the Lorentz group is spin 11.1. Now, I'll give you two reasons why I think the unification in spin 11 is obvious. As I've just said, each of the 32 fermions of spin 10 is itself a Weil spinner with 2 degrees of freedom transforming under the Lorentz group for a total of 2 to the 6 fermions. And the smallest spin group that contains 2 to the 6 fermions, and including one time dimension, because there is a time dimension in the Lorentz group, is the group spin 11.1 of rotations in 11 plus 1 space-time dimensions. And the second obvious reason is that spin 10 chirality, left or right-handed, coincides with Dirac chirality. When physicists talk about right and left-handed electrons, you're usually talking about whether the boost and the spin bit, something to do with the Lorentz group of the Dirac spin, are aligned, it's right-handed, or anti-aligned, left-handed. But that same handedness is duplicated in the standard model, because the weak force interacts only with left-handed things. So that means that one can embed spin 10 and spin 3.1 in only 11.1 dimensions. When you do that, you have to have one extra bit, which I call the T bit, and I've painted it gold because it's the most important bit. It's the time bit. And now this contains all of the spinners of the standard model, including their Weil and internal degrees of freedom. And some lovely things happen. For example, if I flip the T bit to down, this is the right-handed neutrino, I flip it to the left-handed anti-neutrino. Okay. The coincidence of Dirac and spin 11.1 chiralities is a mathematical thing. Okay, Tejinder, I see you've raised your hand.
Just a quick question. Do you have one fermion generation or will you have 3 fermion generations?
Right now, I have one fermion generation, and I'll talk about the 3 generations towards the end of the talk. Okay?
Thank you. Thank you. Thank you.
I will cover them. But this coincidence of chiralities is a mathematical thing. It is a coincidence of the pseudoscalars of the Dirac and spin 11.1 algebras, or correctly, this is now a Clifford algebra. The pseudoscalar is the product of all the 4 vectors of the Dirac algebra in the Dirac case, and in Clifford 11.1, it's the product of all the 12 vectors. The 12 vectors, there's 6 bits, and with each bit is associated a pair of vectors which form real and imaginary parts of a complex vector. So, for example, gamma t minus and gamma t minus. Gamma t minus is the time vector, and gamma t plus is its spatial partner. Right, so now at this point, I've said that works, but one actually has to check that the mathematics works out, and it does. And I could fast forward this, but let's just go through this a little bit. First of all, whenever there are spinors in a space-time, there is an associated Clifford algebra. That's just the way things are. And the relationship between the four Dirac algebras, the four Dirac vectors, those are the vectors of the Dirac spin 11, the Clifford 3-1 algebra, are related to those in the Clifford 11-1 algebra in the following way. These are the four Dirac vectors, and this is their expressions in the Clifford 11-1 algebra. And again, gamma k plus and gamma k minus comprise the real and imaginary parts of a complex vector. Whenever you have spinors, they come equipped with a complex structure inevitably. You notice the time vector is this one here. It's a vector in Clifford 11-1, but the three spatial Dirac vectors are all pentavectors. They're multivectors of grades 5. And you can check that the inner products and Lie algebra of those four Dirac vectors are precisely those of the Dirac algebra. And the standard model algebra is a subalgebra generated by the bivector products of those vectors with the k running over the 5 bits of spin 10, Y, Z, RGB, weak and color bits. And the key point that is important here is that the Dirac and standard model algebras are mutually commuting subalgebras of the Clifford 11-1 algebra consistent with the Coleman-Mandula no-go theorem. The Coleman-Mandula theorem says that the only way to combine internal and space-time groups is as a direct product. And that has been taken to mean that, oh, the grand unified theory has to be a direct product. That's not what the Coleman-Mandula theorem. The Coleman-Mandula says that the symmetries that are realized, the internal symmetries, must commute with those of space-time. And they do. Now, there's a trick that makes this work, which is that you have to take all the imaginary bivectors, that's plus and minus, plus plus would be real and minus minus would be real, but you have to multiply the imaginary bivectors by the color chiral operator, or equivalently, the color pseudoscalar. And that color pseudoscalar, IRGB, generates a spatial rotation in the transverse gamma 1, gamma 2 plane. I showed you previously there was the coincidence of the pseudoscalars, and they can be resolved into a commuting boost and rotation on the Dirac side. And in the case of the rotation on the Clifford 11-1 side, it's the color pseudoscalar. That's where that comes from. Where did I go? Let's go on. So the presence of that IRGB, its addition to the imaginary bivectors, ensures the commutation of Dirac and standard model algebras. Now, I've declared that the Higgs field, the tachyon, is the Higgs field. In a paper that got published last year, we showed that in a spin 11-1 or Clifford 11-1 theory, the minimal Higgs field associated with a minimal symmetry breaking between a spin 11-1 and the present time is a Higgs field transforming in the adjoint representation of the gauge group. And of course, that is exactly like the case of tachyon. The tachyon is a multiplet of the gauge group in the adjoint representation of the gauge group. In the standard model of cosmology, vacuum energy has decayed. It has been unstable, starting with grand symmetry breaking all the way down to the present time. A leading idea of modern cosmology was that right at the very beginning, there was a period of inflation driven by the vacuum energy of hypothesized grand unified field. And grand symmetry breaking allowed that energy to decay into other forms of energy. And in Clifford 11-1, there are subsequent symmetry breakings through the Patti-Salam group, through the electroweak group, down to the present time, where there's a tiny cosmological constant, still some remnant perhaps of the vacuum energy. So this is a predictive theory. It's quite constrained. It's Clifford 11-1, and it so happens that it contains the Higgs fields that we know about, in particular the electroweak Higgs field. Steven Weinberg in 1967 came up with the electroweak symmetry breaking Higgs field mechanism, which seems to have worked. That is now become part of the standard model. And in Weinberg's theory, the electroweak Higgs field is part of a 4-component multiplet. One of those components acquires an expectation value, and the other 3 components are absorbed by the W plus, minus, and Z bosons to give them mass. And that 4-component multiplet is built into the Clifford 11.1 algebra. You don't have to invent it. It simply is there. It's a bivector, which contains a T part, and then there's a weak part. There's a Y and a Z thing, modified by the color pseudoscalar as usual. And that Higgs field, the one that acquires the vacuum expectation value, it carries 1 unit of Y charge, and it gives mass to fermions by flipping their Y bit. Very beautiful. Clifford 11.1 predicts an intermediate unification to the Paddy-Salam group, spin 4 cross spin 6, where a certain set of the 3 coupling parameters, hypercharge, weak, and color parameters, satisfy this relation right here. And so one can go through the standard process of looking at the running of the coupling parameters from the present low energy time, and that combination of coupling parameters hits 1 at 10 to the 12 GeV. So the prediction is there should be unification or symmetry breaking to Paddy-Salam at 10 to the 12 GeV. And then on up to grand symmetry breaking. The Clifford 11.1 algebra contains a field which has all the properties needed to be the grand Higgs field to break spin 10 to the Paddy-Salam group. It also is a bivector. This one is a product of the 2 time vectors, again modified by the color pseudoscalar. And that grand Higgs field does a bunch of things. Amongst other things, it breaks T-symmetry, and it generates a Majorana mass for the right-handed neutrino, which is a good thing. And it predicts grand unification when the weak and the color coupling parameters meet. Now, the hypercharge one disappears into part of the weak force as at Paddy-Salam symmetry breaking. And then the SU3 below Paddy-Salam symmetry breaking, and then spin 6 above it. And the prediction is that those meet at about 10 to the 15 GeV. 10 to the 15 GeV is less than the lower limit of 4 times 10 to the 15 inferred for spin 10 models from the super Kamiokande lower limit on the proton lifetime. So it might be that Clifford 11.1 is already ruled out by observations. However, I'll point out that I made a very abrupt adjustment at the Paddy-Salam scale, and if it's a little bit gentler transition, then that unification could be perhaps postponed to 10 to the 16 GeV, which would definitely be consistent with observations. More work has to be done, but this is something to do with experiment and comparing with observations. Some comments about space-time before grand symmetry. And you say, wow, are you mad, Andrew? You've gone up to grand unification and now you're going before then? Yes, I have to, because we're messing around with string theory. And actually, we have a very precise theory, Clifford 11.1, and it makes some predictions. So let's see what they are. First of all, I'll remind you that Clifford 11.1 is larger than the algebra generated by spin 11.1 bivectors themselves. The standard model bivectors have grade 2, but the generators of the Lorentz transformation in that expression for the gamma matrices, the Dirac gamma matrices in terms of Clifford 11.1 matrices, the generators have grade 6. And the smallest group that contains multivectors of grades 2 and 6 is the subgroup that Shirokov calls G2 of multivectors of grades 2 mod 4, which includes 2, 6, and 10. In 11+1 spacetime dimensions, that group is isomorphic to the symplectic group of dimension 32 over the field of complex numbers. The subgroup, the transverse subgroup associated that goes down to spin 10, that's the, that is G210, which is isomorphic to U16. And that U16 itself breaks down into a product of a U1 vector and an SU16 subgroup. And that SU16 group is the one that says, here I am, I can be, and there's no reason to say it can't be, I can be the symmetry group, the gauge group, before grand symmetry breaking. And that U1 group is generated by the 10-dimensional pseudoscalar and can be interpreted as generating a spatial rotation in the transverse gamma 1, gamma 2 plane before grand unification. What I'm saying is that the relationship between the vectors, the gamma vectors, and those of the Dirac vectors and those of Clifford 11.1 is different before and after grand symmetry breaking. And this is very much connected with the behavior of the grand Higgs field. So this is what the relation is before grand symmetry breaking. And you notice that the time vector is again a vector, but this time the longitudinal vector is just the spatial partner. It's also a vector. It's the spatial partner of the time vector. And then gamma 1 and gamma 2 are pentavectors as before. You can compare it to this relation. You see after grand symmetry breaking, gamma 3 is a pentavector. And here is just a vector. So it's similar. The difference, the basic difference, is that before grand symmetry breaking, the transverse spatial rotation is generated by the 10-dimensional pseudoscalar, and after grand symmetry breaking, it's the color pseudoscalar. Bottom line of this is that space-time remains 3+1 dimensional both before and after grand symmetry breaking. And the Dirac and gauge algebras are mutually commuting subalgebras of the Clifford algebra, but both before and after grand symmetry breaking, again consistent with the Coleman-Mandula no-go theorem. On to the string theory. Bosonic string theory requires 26 dimensions to ensure that conformal anomalies vanish. Now, what we have is Clifford 11.1, that's the algebra that we're working with. So it looks like we're 12 dimensions, but I've told you where those dimensions come from is they come from the spinors, because a representation of one generation of spinors is that of Clifford 11.1. And I've also told you that the fermions live on a D-brane. So it better be that D-brane fills out 11 plus 1 dimensions. And that means that 26 is 14 more than 12, and so something has got to give. There's a precedent for this. It's called heterotic string theory. Heterotic string theory combines left-moving bosonic strings with right-moving fermionic strings. And bosons have to live in 26 dimensions. Fermions have to live in 10 dimensions. So there's a 16-dimensional discrepancy. And Gross et al. Solved that by compactifying the 26 dimensions on a self-dual, on a torus of dimension 16. And there are two possibilities, the rank 16 groups E8 cross E8 or SO32. Those are the two heterotic string theories that emerged from the mid-1980s. Now, in the present case, the grand Higgs field not only breaks T-symmetry, but by virtue of this the color pseudoscalar factor, it also breaks that gauge group before grand symmetry breaking to SU8 cross SU8. And SU8 has rank 7 plus 7 equals 14, which is the dimension of the torus that we would like. So again, it's saying, here I am. I'm the torus on which you should compactify me. So the conclusion is Clifford 11.1 bosonic string theory achieves 12 dimensions by compactifying 14 of its 26 dimensions on a self-dual torus of the rank 14 subgroup SU8 cross SU8. I've used the words self-dual. It is a feature of string theory that compactification tori need to be self-dual. Self-dual means that the determinant of the Cartan matrix is 1. And a standard SUN torus is not self-dual, but if you replace one of its roots by a spinor root, then it becomes self-dual, and that allows winding numbers and momenta on the torus to be dual as required by the modular invariance of string theory. Okay, all of this is rehearsed from Gross et al. They had the same issue, and they had the same solution. They substituted a root of SO32 with a spinor root in order to make it self-dual. And at the bottom there is a little diagram which shows the simplest example, which is that of SU3, but I'm not going to go into it. So the bosons live in 26 dimensions. The fermions live on a D-brane that has to fill out 12 dimensions. Now there's 10 compact dimensions, which are these ones with running over the 10 bits of the standard YZRGB. And the D-brane, the fermions live on the D-brane, which undergoes transverse oscillations in the time and longitudinal directions. That's this thing. So if the compact D10 brane is Riemannian, it forms a manifold, then its holonomy group must be a subgroup of SO10, or more correctly, of the covering group spin 10. And if spin 10 is broken, then the holonomy group must be a subgroup of the remaining symmetry group. Spinors have a natural complex structure, so that 10-dimensional compact manifold is a complex manifold, and a manifold with n complex dimensions, equivalent to 2n real dimensions, is called an n-fold. And there is a specific type of complex manifold of particular interest called Calabi-Yau manifolds, which have SUN holonomy, and the Calabi-Yau manifold has the signature property of carrying zero energy momentum, which is like the universe, the vacuum that we live today. If our vacuum is full of contains a D-brane, it better be a Calabi-Yau manifold so that it carries more or less zero energy, as we more or less see bar a cosmological constant today. Okay, so before grand symmetry breaking, the holonomy group is spin 10 on the compact D10 brane. That breaks to the Patti-Salam group at grand symmetry breaking. And Durand's theorem says that if the holonomy group is a direct product, then the underlying manifold must also be a direct product. So the 5-fold here splits into a direct product of a 2-fold and a 3-fold. And then at Patti-Salam symmetry breaking to the standard model, spin 4 and spin 6 break down to the standard model, and the SU2 factor produces a Calabi-Yau 2-fold, and the SU3 color factor gives you a Calabi-Yau 3-fold. And the U1 doesn't actually contribute to the manifold, and again, this is something to do with the Durand theorem. Then later electroweak symmetry breaking gives us the symmetries that we see today, leaving us with a Calabi-Yau color 3-fold at the present time. So that's kind of neat. The standard model is telling you you're ending up with a Calabi-Yau manifold, and that's exactly the kind of manifold that one would like to see in today's universe. There's some magical things that happen along the way. Remember that bosonic string theory has to live in 26 dimensions, so it has 26 coordinates, which consist of the time coordinate, the longitudinal coordinate, the direction that the D-brane is wiggling, the fermionic D10 brane, the compact D10 brane, and then a 14-dimensional bosonic torus. One follows the usual process that you can see in textbooks of quantizing the string. And what you do is you first gauge transform the string metric to be conformally flat. And then you can do a Wick rotation to a conformally Euclidean complex scale and replace the two string coordinates by a single complex coordinate and its complex conjugate, Z and Z bar. And in curved space-time, the Nambu go-to string action implies this covariant string wave equation. You notice it's got some coordinate connections, also known as Christoffel symbols. there. So this is fully covariant, valid in a curved space-time. Usually in string theory, one goes directly to Minkowski space-time, in which case this goes to zero, the connections all vanish, and the general solution to the vanishing of this is a sum of holomorphic right-moving and anti-holomorphic left-moving modes. But in a curved space-time, the wave equation also has open string solutions in which all modes are right-handed functions only of z. They're holomorphic. And in that case, this goes away. So the connection term again vanishes. And the solution for this is just right-moving modes. Again, you follow the usual standard quantization path of string theory. And you expand the coordinates as functions of this holomorphic string coordinate. The K and the L are dual momentum and winding modes on the 14 torus, and the alphas are creation and annihilation operators for a ladder of Kaluza-Klein modes. And the Z can be interpreted as a Fourier mode. And then quantization carries through in a curved space-time exactly as it does in Minkowski space. So I thought that was a very beautiful piece of mathematics that just allows me to have a curved compact manifold without any problems. There's some other things that I thought were beautiful and magical. One of them is that it turns out that the things that we're interested in, the symmetries of Clifford 11.1, are generated by anti-commutators of spinors. Let me remind you that the Brouwer-Weil 1935 theorem states that the algebra of outer products of spinors is isomorphic to the Clifford algebra of multivectors of all grades in any number of space-time dimensions. Now, I have told you that the thing of interest in Clifford 11.1, the symmetries of interest, are those of multivectors of grades 2 mod 4, which I'll call bivectors, but they're really 2 mod 4. And it turns out that the bivectors are generated by like-handed anti-commutators of spinors, column spinors with row spinors. And the other thing that happens in this thing is there's geometry. There's a 10-dimensional fermionic geometry, and there's a 14-dimensional torus. And the vectors are also generated by anti-commutators of fermions, and they're oppositely handed in that case. So Clifford 11.1 shares with supersymmetry the property that symmetries are built on anti-commutators of fermions. But the difference is that Clifford 11.1 symmetries agree with those observed, whereas supersymmetries do not. I find this very cute. It kind of suggests maybe spinors can be the fundamental building blocks of space-time, and that's an idea that it's been explored by many people, including Roger Penrose, loop quantum gravity, and so on. Kind of cute. Of course, the signature feature, the signature promise of string theory is that it delivers spin 2 gravitons as part of the theory. They appear naturally as massless eigenstates of closed strings. Now, in Clifford 11.1, the closed string has no ends that can terminate on the fermionic D-brane. So it must be a scalar under gauge transformations. And by that, I mean not just charge-free, but a complete gauge scalar. By contrast, for example, the photon carries no charge, but it's not a gauge scalar because it transforms non-trivially under a gauge transformation, under the electromagnetic gauge transformation. So this horrible expression, it's not that horrible actually, is the expression for the graviton in Clifford 11.1. All it is a trace over tensor products of right-handed massless gauge bosons with their left-handed t-bit flips. It looks complicated, but there's just 2 components there, a left-handed and a right-handed spin 2 graviton. And the graviton is its own antiparticle. The other particle that belongs in the closed string spectrum of Clifford 11.1 is a spin 0 dilaton. Again, there's 2 components, and it is its own antiparticle. One of the key properties of any viable string theory is that gauge and gravitational anomalies vanish. And I'll remind you that historically, the vanishing of anomalies in a supersymmetric string theory was a thing that precipitated the first superstring revolution. Supersymmetry demands a Majorana spinners of just one-handedness, and it requires, as I write here, a heroic cancellation of anomalies between fermionic and multivector boson fields. It's absolutely remarkable that happens. It looks like somebody pulling a rabbit out of a magician pulling a rabbit out of a hat. By comparison, in Clifford 11.1, the vanishing of anomalies is almost trivial. The fermions come in chiral pairs, right and left-handed fermions coming in matching conjugate representations. And a sufficient condition for anomalies to vanish is that they come in matching representations of opposite chirality. So it's a straightforward thing that happens. Onto the fermions, about which Tajinder you had a question. There are 3 generations of fermions in the standard model, but only 1 generation of bosons. And to me, that suggests, and I think to other people, it also suggests that the generations are not just an extension of symmetry. Now, in string theories with fermions living on a compact internal manifold, as here, the number of generations equals half the absolute value of the Euler characteristic of the complex manifold. This was realized already back in 1985 in a very influential paper by Candelis et al., which suggested that this is the way to get 3 generations. The first 3-generation Calabi-Yau threefold was discovered by Yau back in the 1985, I think, yes. And since then, many other, not a myriad, not 10 to the 500, but many other Calabi-Yau threefolds with 3 generations are now known. This is my summary. I'm not going to read all of it, but I'll read the first point because, again, this is the thing that I want you to take away from this lecture today, which is that contrary to common wisdom, string theory does not require supersymmetry. Abandoning supersymmetry offers a path forward to a string theory that actually agrees with reality. And I invite you to have your own go at saying this is right or wrong. You're welcome to it. I'll stop there and I'll take questions. And thank you very much, everybody.
Great. Thanks so much, Andrew, for making it exciting. Good to go back and have a fresh look at string theory. So the talk is open for questions. Please go ahead. Use the raise hand feature. And while the questions come up, Andrew, maybe could I ask you something about the graviton? If you could kindly go back to your point 17, it was the gravitons?
Yes.
Item 17 or 6? Yeah, yes. So your first statement, of course, we all know it's great. A spin 2 gravitons, as you said, appear naturally as massless eigenstates of closed strings. And in your third paragraph, you would you say that this also arises naturally in the same sense as that of the first sentence?
Yes. The closed string is a tensor product of open string eigenstates. But the difference, so the standard string theory, superstring theory, actually puts the graviton as part of believe it or not, a 256 component multiplet. There's at least in maximal supersymmetry, there's a graviton partners to the gravitino partners, which are spin 3 half partners to the graviton. In this particular case, those extra fields disappear because the closed string has no ends that confirm that no fermionic ends, so it must be a gauge scalar. And so you're left with just 2 component gravitons. But otherwise, it's the same as in standard string theory.
And the open string also admits a spin 2 graviton as one of its excitations. Is that what you're saying here? By taking the
What we're talking about is what are the massless eigenstates of the spectrum of the string. There's massive eigenstates, but the ones of interest in the low energy physics are the massless ones.
right.
And for the spin 1 things, those are the gauge bosons. They have spin 1. But there are massless gauge bosons also that are tensor products of left moving and right moving eigenstates. Again, and so they're a tensor product.
And
So
the left moving and right moving eigenstates are spin 2 each.
Yes.
Okay, thank you. So 2 questions. David, go ahead first, please.
Great, thanks, Agenda, and thanks very much, Andrew, for the talk. This question is coming very much from a non-string theorist. It's about the kind of uniqueness of this kind of non-supersymmetric approach. So in M theory, there's a famous plot showing these 5 or 6 branches of these different superstring kind of possibilities all related by dualities. If you take the non-SUSY approach, are there similar 5 branches, or how many branches are there in this case?
Yeah, I have to say there's a part of me that loves supersymmetry because it's such a beautiful theory.
Right.
I have a suspicion that somewhere in the multiverse supersymmetry happens, but apparently it doesn't happen in our little neck of the woods. That's just my opinion. My opinion is motivated, of course, by the observations and the experiment that says no, supersymmetry is just not happening. Now, the whole setup of all the groups, it kind of suggests to me that maybe there is a link between what I'm talking about and M theory and the other thing. But I haven't tried to go in that direction. I have tried very hard to think about accommodating spin 11.1, for example, in a supersymmetric theory. And in the end, I gave it up. It was quite impossible. So I don't know the answer. I've sort of, the way I've moved is, okay, I've convinced myself I have to abandon supersymmetry. Now, what is the simplest thing that I can do that agrees with observations and experiment? And it's a very compact thing. What I've put forward here is actually much more minimal than the so-called minimal supersymmetric standard model, which is really not minimal at all because it contains all these vast number of extra fields. There are some extra fields in Clifford 11.1, which I haven't talked about, but there's not very many of them. Most of the fields are ones that we either already see or are really a nice extrapolation, like the right-handed neutrino.
Okay, great. Thanks. So just a related question. So having fewer fields and so on, are things like the landscape problem kind of less severe in this case, or how does that stand for this non-supersymmetric case?
Yeah.
Sorry, which
landscape?
The landscape problem for
sorry.
superstring.
Okay.
So the landscape, my understanding is the landscape is supersymmetric. And what I'm saying is the reason you haven't made any progress with the landscape over the last 20 years is that you've been focused on insisting on having supersymmetry. And supersymmetry not only requires all these extra superpartners, which are not seen, but it also requires breaking supersymmetry at some level that apparently is above what we're able to observe. And there's many different supersymmetry breaking things that you can contemplate. So there's this vast number of possibilities that can happen. And I've taken the point of view, no, let's move out of the landscape. I'm not saying it's wrong, but if you move out of the landscape, out of the wilderness, maybe you can get to the promised land. I don't know.
While at that, could I just ask a question, David, if you don't mind?
Sure, of course. Yeah. Sure.
So just to take part with you in the discussion. So in the 1984 revolution, would you say they took us on a wrong path when they said that string theories have to be supersymmetric? In what way is the current spin 11 any less quote unquote beautiful or natural than, let's say, E8 cross E8?
Well, I'll go back to where it was. Was it this thing or this thing? Yeah. So if you go back to history, the original history in the 1970s, string theory was being contemplated as a theory of the strong force. And it failed as a theory of the strong force because, amongst other things, it predicted that that above the strong force scale, it predicted what the behavior of cross sections at high energies would look like. And it turns out that they fall exponentially, and that was not what was seen in observations. The observations seem to show that high energy cross sections went off as a much more slowly as a power law. And SU3 came along, and SU3 predicted what was seen. And when de Hooft discovered that asymptotic freedom, that SU3 was asymptotically free, it explained why the meson, when you've tried to pull it apart, it just broke apart into more mesons. That's the pion. And so it no longer needed to look like a string. So string theory was predicting the wrong thing, and SU3 was predicting the right thing. So as of 1974, the standard model really solidified, and it's been solidified back then. Any modern theory of the standard model has to respect the U1 cross SU2 cross SU3 thing. What has changed, though, is what I'm saying is if the string theory scale is up at the grand unified scale instead of the strong force scale, then instead of considering SU3, one needs to consider a grand unified theory, such as spin 10 is the most obvious choice. So, okay, so after 1974, basically string theory was abandoned, except for a small number of people, including Michael Green and John Schwartz, and they kept working on it. And they eventually, they were faced with the problem of this tachyonic ground state. And so they started looking at supersymmetry. And the original stumbling block was that it seemed that type 1 string theory, which was the first string theory, supersymmetric type 1 string theory, it seemed to have gauge anomalies. And then they showed that by this magic of including fermions and bosonic fields, one could get the anomalies to vanish. And that was the first superstring revolution. And very quickly, a lot of people came on board. So I understand that supersymmetry was absolutely crucial to those first advances. But that doesn't mean to say that in retrospect it was right. I think one has to challenge the theories against what we see at the present time. And those include the failure of the Large Hadron Collider to detect any evidence of supersymmetry at a TeV or so.
And in the mid-90s, when Polchinski and later others showed D-branes, discovered D-branes, that was another opportunity to drop supersymmetry and go back to the bosonic string, but which you have done now. So that was also not noticed then?
Yes, I find it a little bit strange. There's definitely the case that Polchinski in 1995 proposed D-branes, and his D-branes were definitely supersymmetric, so-called BPS branes. There's no question of that. And I quoted from his paper of 1996, where he says you absolutely need supersymmetry. And you can look at Polchinski's book, and it contains words which are actually very similar to those that you're still seeing on the screen here. They reflect the Green, Schwartz, and Witten book. And Polchinski goes through the same arguments. He even has the same picture of a quark and an antiquark joined by a string. and he calls them Chan pattern degrees of freedom, the quarks, and the gauge bosons he calls Chan pattern factors, and he never calls them fermionic. And I keep thinking, Joe, you can see that this is fermionic. Why don't you just declare it is? You could have powered through it that kind. So I find it very difficult to understand why this were non-seen. And part of me hopes that somebody is going to point out to Andrew that, Andrew, you're just being stupid here. You're misunderstanding this. But I've been spending quite a lot of time on this. And as far as I can see, the mathematics that I'm talking about is absolutely robust. So if you're going to argue with me, you need to argue with me mathematically and not based on authority.
There are other people also who are now studying non-supersymmetric string theories. There are several people doing that now, right? Isn't it?
Yes, there's quite an industry on so-called non-supersymmetric theories, but those don't abandon supersymmetry altogether. Those involve having supersymmetry at some very high energy scale. And there are a number of so-called non-supersymmetric, but what they really mean is broken supersymmetric models without any residual supersymmetry.
Okay, broken at some very high energy scale, yes.
Yes. So when, for example, Lenny Susskind talks about non-supersymmetric things seeming to fail, he's talking about non-supersymmetric, meaning broken supersymmetry.
Okay, thank you. David, sorry I interrupted you. If you have anything more to say before
I think that's all. I think I'd want to ask about uniqueness, and the impression I'm getting is that, Andrew, you do think that this non-SUSY approach is more unique than the vastness of superstring theory.
I'll say that the minimal version that I've put forward here, it does seem to me this is the minimal version, and you can add bells and whistles if you wish, and you're very welcome to do so.
Thank you.
Okay,
thank you.
Yeah, great. Thanks very much. Thanks.
Anthony, please go ahead.
Okay, thanks very much for the talk. I have a couple of related questions. The first is on the theme of minimalism. So you've got the proposal for Clifford 11.1, and of course I'm a big believer in Clifford algebra as the route through to unified theory. If you've already got Clifford 11.1, you can do a great deal with that, which you've been showing us some of. Is it, in your mind, absolutely necessary to then move on to the string theory side of it? Why can't we just have Clifford 11.1 as a unification group, and then let's see the consequences of that? Why do you need the rest?
Because one needs a quantum theory of gravity. And in my opinion, it does seem to me like string theory is the most prominent direction to go. So I followed your path of grand unification. And then it seemed to me, okay, you have to have string theory. It doesn't seem to me, I'm sorry to be rude about loop quantum gravity. I like aspects of it. It's got the algebra of spinors going for it. Never mind about that. But it does seem to me that string theory really is the most promising theory of quantum gravity out there. And that is the direction that I have tried to pursue. And as you have seen, a number of things that I found were quite magical have happened along the way, which persuade me that maybe this is something worth considering.
Okay, so you don't think at the moment there's another route through to quantum gravity than string theory?
I'm not saying that. I think this is the most promising thing. And it's the one that I've been spending the last 2 years thinking about very deeply.
Okay. Well, the other question is related to what Roger Penrose has said a few times in earlier talks in this series. And I think it's the thing that upsets him most about what happens in string theory, which is the huge increase in functional degrees of freedom which you have, because you have all these space-time coordinates, coordinates which are full functional degrees of freedom. You can compactify 14 of them or whatever, but then you still have each of those initially has got all the degrees of freedom associated with a continuum, and this is in a huge number of dimensions. And so I mean, Penrose definitely speaks out very strongly against that aspect of string theory. Did you have any comments on that?
Yeah. So go back to this slide talking about anti-commutators of spinors, basically generating all the pieces of the Clifford algebra that seem to be required in this particular theory. So I am definitely, from a philosophical perspective, sympathetic to a Penrosian idea that really it's spinors that are the fundamental building blocks of everything. You look around, and in physics, we're all made of spinors. And all the gauge groups of the standard model, including and general relativity, they're all gauge groups based on symmetries of spinors. So it's pretty clear that as far as nature is concerned, spinors, which are the fundamental representation, there's no smaller representation of rotation groups, those things are really fundamental. And I'm sympathetic to the idea that one can maybe dig even deeper. This is string theory. Maybe there's a deeper level by going into spinors.
Okay, but that seems to be then saying that you're not happy with some aspects of string theory, looking for an alternative here then.
I can tell you what my motivation is. I'm an astrophysicist. I'm interested in the extreme things that happen inside black holes. I'm interested in a theory that I can actually use. And so my primary goal is I want a quantum theory of gravity that I can use, and you string theorists are not providing me one. I apologize for venting a little bit of frustration there, but that's where I'm coming from. I actually want to apply this in a regime where grand unification is happening and where Planck scales are being reached. I'd like to apply this thing to what I would call reality of real black holes in our real universe.
Okay.
Just wanted to mention one thing, Andrew. There is another line of thinking taking place among some people that the spin to nature of gravity is emergent. What is more fundamental is that there is pre-gravitation, which is like Yang-Mills gauge theories of spin 1 gauge bosons, or SU2R analog of SU2L, the weak part of electroweak. And to my mind, maybe that is the one thing that string theorists may have missed. There's no reason to think that general relativity as a spin to theory is fundamental. It may be effective and emergent, and we should try to understand why gravity is not more like Yang-Mills. That nobody has really addressed that. I mean, yeah, just a comment.
Okay, well, you can see that I have followed the standard string theory route. There's no question that in string theory, one can enumerate what the massless fields are. And there are the massless gauge bosons of spin 1, and then there's the massless objects of spin 2, and also the dilaton. And those just come out.
I agree, but I think string theory, if it is a theory of quantum gravity, it also has to be a theory of unification, because fermions are present and the other interactions will also be switched on. That was the argument that string theorists used to give against loop quantum gravity. You cannot quantize gravity unless you also have other interactions brought in and unified. I think you are trying to do that. And to me, the failure of string theory is that they say now it's a theory of quantum gravity, but they don't say anything about unification and the standard model. But all these have to come together. So if in your picture it comes out, of course, it's great. But I'm saying that it's not a bad idea to question whether spin to gravity nature is fundamental or emergent.
Yeah, again, I'm all in favor of everybody coming in here and exploring this. I think the idea of just getting rid of supersymmetry altogether needs to be something that is thought about by more people. It may be a way
Yes,
forward.
I totally agree with that. Yes, I totally agree with that. Yeah, thank you, thank you. I think Anthony, something more?
Not right now.
Okay, Francesco, sorry to keep you waiting. Please, if you are there, please go ahead. I wonder if Francesco has left. Yeah, I'm sorry. I think Francesco has left. So I wanted to read out at least one comment from your Froelich. One might want to give some credit to Joel Shirk for having anticipated D-branes, but not viewing this possibility to be realistic. You want to respond to that, Andrew, for Shirk's contributions?
I would agree with that. I apologize for not giving Polchinski all of the credit.
Okay, thank you. Thank you. And Bernd, you want to take up the points you mentioned, or should I read them out?
I can also read them out now that I'm here. So
Yeah.
thank you, Jinta, and thank you, Mr. Hamilton, for the nice talk. I have a question concerning the rule of fermions in string theory and higher dimensional theories. I think the issues goes a little bit back also to Kaluza-Klein theory. They always had trouble with putting fermions into the Kaluza-Klein theory. Either you have to change the geometry, so explicitly introduce a spinor geometry, or you have to introduce fermions as singularities in the manifold or something. I think this is also one of the reasons why people looked for supersymmetry, or at least for a modification of the original Kaluza-Klein idea to get a geometric handle on fermions, or to avoid just introducing them as singularities. This is one of the reasons why people also, looking for modifications of the original Kaluza-Klein idea. So before I go on to my next question, is this correct? Would you like to respond to my remark or to my question?
Yes, the string theory, well, I mean, the string theory that I proposed here, Clifford 11.1, actually looks an awful lot like the heterotic string theories with a compactification torus very similar to that. And that compactification torus includes, where is it? Gone, 8. Do I want that? This one here. I don't know. The compactification torus has its modes. There's Kaluza-Klein modes on the compactification torus, and there's one for each dimension. So in heterotic string theory, that would be 16 of these things, and they form a ladder of states, one of which is massless, and then you go up to higher levels. So there are those Kaluza-Klein things, but there's also the winding modes and the momentum modes on this torus. The torus is combined. It's not flat. It's combined in a non-trivial way, and so that allows for these other modes which are non-Kaluza-Klein. But that's on the bosonic torus. The place where the fermions, I find them anyway, are on this 11 plus 1 dimensional fermionic thing, whose compact dimensions fill out 10 dimensions. And there are actually some Kaluza-Klein modes on that Calabi-Yau D10 brane. There's 10 of them to be specific, and those Calabi-Yau those Kaluza-Klein modes they duplicate in some ways the ones on the bosonic torus. But the Calabi-Yau manifold is a much more complicated thing than a flat torus. So it's not just, its modes are not just the Calabi-Yau, it's not just the Kaluza-Klein modes that play a role. And that the
Okay.
fermionic modes, you can put fermions on the Calabi-Yau manifold, and you can write down the Dirac equation, you can write down an action, and you can solve that. And you get the usual story about zero modes, and the number of zero modes and the number of dimensions, sorry, the number of generations and so on and so forth. So this
Okay.
is something that has been relatively well explored in the mathematical literature because there's a huge amount of interest in Calabi-Yau manifolds.
Okay, thank you very much. I will come back later with my question, but now Francesco is back.
Francesco, go ahead, please.
Yes, thank you, because yes, I'm back because I had some problem with the connection. Can you hear me?
Yes.
Okay. Yeah. So thanks for the fascinating talk. It was quite stimulating in part and quite interesting. I have just some comment concerning some a question which was done before, because the web of dualities from M algebra in 10,1. So if you play your game to put also the bosonic theory, the M theory is in 10,1 dimension. You have Majorana, but there is also the F algebra version, which is with Majorana Weilspinor in 10,2. 10,2 is the conformal algebra of 9,1 for the standard 10-dimensional string, while your version 11,1 is a conformal algebra of the Euclidean version in 10 dimension. And it looks like in some sense you have some de Sitter version, while the F algebra is an anti-de Sitter version. And I wanted to point out that there was some paper in the middle of the 90s, I think it was, if I correct, 97, by Setskin, in which he investigated superior means. The maximal that you can get is in 11,3 dimension, 14 dimensional space. So it looks like maybe to pursue this web of duality, one should go further up to this case that 11,3 that can encompass both 10,2 and 11,1. You have some idea, you have seen look in this direction.
I want to comment. Sorry about that. I do agree that this spin 11.1 thing or Clifford 11.1 thing is definitely not the only direction in which one can go. There have been others who've proposed Clifford 11.3, for example, and that's a possibility. You mentioned a whole bunch of things here, and I'm not sure that I'm really qualified to comment on everything that you have said, but I would just encourage you, by all means, go ahead, because it seems to me that this is relatively virgin territory which needs some more plowing.
Definitely, that's the fascinating story. There is some mathematical structure that underlying all these, and it is not yet completely understood. That's the point. That's
okay.
And it looks like you have some new pieces in this web of duality. That is really fascinating. Thank you very much. Mm-hmm.
I would much appreciate learning more about this.
Thank you, Francesco. Andrew, I wanted to ask another. No, someone else. Won't you go ahead, please?
So it will be brief, and I guess you already answered my question during the talk. But when you discussed fermions and bosons, you gave some examples of fermionic systems whose center of mass is a boson, or can be described by bosonic degrees of freedom. Are you aware of de Broglie's idea of deriving bosons from fermions, the fusion theory, or the neutrino theory of light by Jordan from the 1930s? So these were early attempts to derive bosons from fermions, or to get bosons from fermions.
I guess I'm not familiar with those, but I'm very sympathetic to the idea of generating bosonic things from fermionic things. Yes.
Okay, that's it. Thank you.
Thank you. Francisco, did you have another question, or should the hand be lowered?
Oh, sorry, I will lower my
Yeah,
hand.
thank you. Thank you. David, go ahead, please.
Right. Thanks again, Jitendra. Thanks, Andrew. It's a very tangential kind of question, but I was curious about this. Andrew, you mentioned that a lot of your interest in string theory comes from the idea of a need for a theory to quantize gravity. That seems to be one of the motivations for using string theory. I'm just curious about what are the main reasons why you think that gravity should be a quantum theory?
Because there's two theories called general relativity and
Right, sure, yeah.
there's general relativity and there's quantum mechanics, and in normal quantum field theory they just don't work with each other.
Right, but there could be something that needs modification with quantum theory rather than gravity. Why the assumption that it's on the gravity side?
I just go with I want to say the simplest thing that I can think of. Again, my motivation as an astrophysicist is to try and understand what really happens inside real astronomical black holes. And there's a part of me that is not really interested in quantum quasi-gravity per se. I'm interested in kind of the deeper questions of like what happens inside black holes and what happened at the beginning of the universe. And in those cases, one is reaching grand unified scales and maybe Planck scales, and you need to have a theory which is able to deal with those things. So those are my motivations.
I completely agree with the need to bring gravity and quantum theory together. I'm just curious why there's usually an assumption that it's gravity that has to be quantized rather than something modified with quantum theory. But
well, it does look like, plain old quantum field theory, particle field theory, plainly is telling us it's an effective theory. I think there's widespread agreement that quantum field theory is an effective theory. Steven Weinberg says this explicitly in his book, for example, and Wilson was influential in pushing that idea. It's plainly telling us there's something going on small scales that we do not understand.
Right.
And small scales involve high energies. And when you apply, okay, I'm just repeating the same old things that people say, which is you need something that reconciles general relativity with quantum theory. If I go inside a black hole, I meet this singular surface where general relativity gives up the ghost. What happens? Does physics stop there? I suspect not. I suspect that it continues. And I suspect, for example, that the evolution of the singular surface of a black hole is unitary, as quantum field theory or standard quantum field theory would require. So that requires apparently a quantum field theory of gravity. And it may be that in the next century, we'll have a better understanding, that right now our understanding is completely wrong and we need something new. But for the moment, we have two pillars to stand on, and one is general relativity and one is quantum field theory. And one would like to put those two things together in a consistent theory of quantum gravity.
No, I agree. I guess I'm just thinking that there are other problems with quantum theory, like the measurement problem or the vacuum energy and so on, that also need to be addressed. So I mean, quantum theory isn't kind of necessarily the final answer, but okay.
Well, yeah. You mentioned the vacuum energy. Yes, absolutely, the dark energy. I've suggested that, okay, this is the tachyon of a string theory, and whether that works or not, we'll have to wait and see. But certainly one of the issues is that it seems that supersymmetric string theory really does prefer an anti-de Sitter universe as opposed to the one that we live in, which is apparently a de Sitter universe. And if you get rid of supersymmetry, it seems like, okay, maybe you can have a de Sitter universe. Again, I haven't explored that, but it leaves an opening.
Okay, great. Yes, thanks very much. Yeah, thanks.
David, could I add something there in trying to add to
Sure.
the discussion you and Andrew are having? And suppose we ask this question that we have a collection of quantum systems, let's say a collection of fermions, which are described by quantum field theory. Can they, between them, give rise to a classical gravitational field described by general relativity? And to my understanding, there are great difficulties one faces if one says that quantum systems can give rise to gravitational fields which are exclusively classical and have no quantum behavior. To my understanding, any description of this kind runs into problems. And for me, that would be one reason for thinking that there has to be something underlying to general relativity, which is a non-classical nature of gravity. But I fully agree with you that this goes back and has an influence on quantum theory, because quantum theory does assume the existence of a classical time. But we just agreed that quantum systems cannot give rise to a classical spacetime. So in that sense, there should be a way to describe quantum field theory without making a reference to a classical space-time background. So from that point of view, quantum theory also needs to be modified by having to give up space-time structure. And my view is that something like string theory, since it has been mostly done perturbatively, works by building around a classical space-time background. They of course know that when they say space-time is doomed, they have to get rid of it, but they don't know how to do it. What is underlying space-time? My picture is that one has to, per se, ab initio, from first principles, write down a quantum theory which is independent of classical space-time. And that is what I would call quantum gravity, a description of quantum theory in which space-time is not classical. For me, that is quantum gravity. And that is not quantization of classical gravity. So it's not quantum gravity in that sense, but it is more primitive because we are now looking at some dynamics which is neither quantum nor gravitational. It is something new from which both these have to emerge. Quantum theory has to emerge and gravity has to emerge. So gravitation and quantum theory are both emergent phenomena, which is what I think you are trying to.
Yeah, that seems a more even description between combining general relativity with quantum theory. It seems a more even-handed approach, maybe.
Yeah, I think now we got to the same language. Yes, I agree with you.
Okay.
But
Yes.
I don't know if that is Andrew's viewpoint. I think Andrew probably would put quantum field theory as more fundamental than gravity. Would you?
Well, we're venturing into more philosophical territory. My own philosophical strategy is to walk slowly up the mountain rather than leap and make some fundamental thing. And maybe as you climb up the mountain, the parts of the mountain start to reveal itself and you begin to understand what the fundamental structures are. I don't know what those structures are. And again, my motivation is I want to use this thing and see where it takes me. So I'm definitely sympathetic to you. And I've shown you on this slide here, the fact that all the things of interest in this particular string theory seem to be emerging from anti-commutators of fermions.
And that's beautiful. I agree. Yes.
Right. And the fermions have this intrinsic quantum structure in them. It's built into a fermion, for example, that it has a Lorentz structure. I think of a Dirac electron, for example, as being a Lorentz gyroscope. You can take a snapshot of it, and it's 8 components, it's 4 complex components, tell you not only which direction it's pointed, it's got a spin direction, but it also determines a rest frame. It's got all of the Lorentz degrees of freedom in there. So here you have this thing which is somehow intrinsically flat. Yes, the the electron is an intrinsically internal flat thing. That's its tangent space is, it's flat. And yet it is somehow producing this emergent curved space-time thing. And that I don't understand. I wonder at it, and when I say I'm wonder at it, I'm in wonder at it, how nature manages to do this. So I don't know. There's a lot more to understand in physics,
I
but
agree.
it does seem to me that we need to try and unblock what has happened in string theory. It seems to have stalled.
Yeah, thank you. Yeah, I just wanted to add a point before handing over to Anthony, related again to what David, the point that he raised, that namely, if we agree that we want to be able to do quantum field theory without making any reference to classical space-time, you are already, when you're working with the Clifford algebra, say CL11.1, you're already very close to the ballpark of division algebras and quaternions and octonions, which are very intimately related to a Clifford algebra, as you of course know. And so what we have been saying is that when we want to replace classical space-time in quantum theory, we'll replace it by a non-commutative structure given by division algebra, say the quaternions or the octonions. And Clifford algebras made from these division algebras are in turn used to make spinors which describe fermions. We totally agree with you that fermions are more fundamental. You should make other structures from them. But we also then relate fermions to Clifford algebras and division algebras. And gravity is there. Once we have a non-commutative space-time described, say, by quaternions, we can easily bring in gravity, and that is where we don't need string theory. We might land up with this theory which looks very much like string theory, but we would arrive there from different considerations by starting with the background space-time, which is already non-commutative right from the word go. Yeah, okay, that's all. So I'll hand over to Anthony now.
Thank you for those comments.
Thank you, thank you. Thank you for listening. Anthony, go ahead, please.
Perhaps ask about something back more on the sort of experimental practical level. So what you were saying about the proton decay, the proton lifetime, that's already getting a bit worrying, as you said. And you've got this possible temporary fix of changing the slope of the transition or the nature of the transition at the energy scale below that. But I wonder if you've thought about more fundamental ways of trying to avoid the proton decay problem. Not all grand unified theories end up with that problem. And I'm just wondering if there's some starting point that's a bit different from where you are now that could avoid it. Have you looked at that?
I'll just say that of all the proposed grand unified theories, the most popular one at the moment is in fact spin 10 or SO10 as they precisely because it pushes the grand unification energy up to 10 to the 16 GeV or somewhere around there. Now, the most naive interpretation of the data from the Planck satellite, the cosmic microwave background, if you from the absence of tensor modes, in the most naive interpretation of the absence of tensor modes, the strength of the tensor modes is related to the density of the vacuum during inflation. And right now, the upper limit of that from Planck is 2 times 10 to the 16 GeV. And again, the lower limit is 5 times 10 to the 14. And that's in the specific context of spin 10 theories. So I'm really hopeful that it's somewhere between that. It's around 10 to the 16 GeV. There are, as you know, there's lots and lots of literature on this very subject. And have I tried to fiddle things more? I haven't. I'm hoping actually that all of the people who do this for a business, you know, go to 2 loops and 3 loops and 5 loops and whatever. I've just done the most naive thing, looking at the running of the coupling parameters and looking at the abrupt transitions that happen. So mine is the traditional naive calculation of the running of the coupling parameters, nothing very sophisticated. There's a bunch of groups doing much more sophisticated work. And I'd like to say, okay, you're welcome. Try it. Have a go. Break my theory. If you break my theory, I'll be quite happy because I can move on and do other stuff. I want to go back into black holes.
Okay, but basically it's a similar result that you get just with spin 10. Is that what you're saying?
I don't know. Spin 11.1 is close to spin 10, isn't it?
Yes. Okay.
Thank you. Thank you. More questions, please? Since you mentioned the inside of a black hole a few times, Andrew, I'm just curious, what are your insights? So what does an observer see when he's falling towards the center? What should he see instead of the singularity?
Okay, do you want me to give you another lecture?
Yeah, I mean, I'm curious. Yeah, do you see, you have thought a lot about this? Yeah, please, go
Yes,
ahead.
I've done a lot of work on this over the last, gosh, pretty much almost 20 years now. I've focused a lot on what's happening inside black holes. And the most interesting thing that happens inside black holes, I'm talking real black holes, real astronomical black holes, is that there's this violent instability that happens at the inner horizon of a rotating black hole, an instability that was first pointed out, curious enough, by Roger Penrose in 1968, when he pointed out, if you're an observer, you go down to the inner horizon. He was talking about a Reisner-Nordstrom black hole, which has inner horizon like a rotating black hole. But he pointed out, Roger pointed out, if you go down, you see the outside universe infinitely blue shifted. And Roger suggested in 1968 that that might destabilize the inner horizon and prevent the chaometric from having anything inside its inner horizon. It would prevent this ladder of universes and all the weird stuff that happens in the analytic continuation of rotating and charged black holes. That was eventually, the nature of that was cleared up by Werner Israel and his graduate student, Eric Poisson, in 1990, who showed that there was an exponential instability that they called mass inflation at the inner horizon. And the nature of this instability, I've spent quite a lot of time thinking about it, is basically to focus ingoing and outgoing streams at the inner horizon to be moving faster and faster and faster. The closer they get to the inner horizon, the faster they move through each other. So one has a situation where ingoing and outgoing streams can reach, if you go all the way to the inner horizon, an infinite gamma factor. And there's nowhere else in the universe where such extreme gamma factors are created. And I find it fascinating that nature is playing this game of throwing things into rotating black holes all the time, and you've got collisions happening at up to Planck energies and possibly beyond at the inner horizons of rotating black holes. The most interesting cases are supermassive black holes because they do the most accretion. And one might well ask, what is happening at the inner horizon of supermassive rotating black holes? So that's kind of where I'm headed in my research, and I could say much more of it if you like. But that's what's motivating me to think about string theory.
Do you need quantum gravity for that? In the final,
Yes, you reach Planck scales.
At the horizon itself? No, we
At
are
the
not.
inner horizon, yes, you do.
We are not talking of the singularity. The curvatures are finite at the inner horizon.
Yes, but there's instability starts the curvature, causes it to start blowing up.
Okay, yes, thank you. I was also interested in the theorist black hole. So when you have a Kruskal-Zekeres covering of the Schwarzschild black hole, there's a mirror image, so to say, inside, suggesting that they are two equivalent universes. So it's like as if you are a freely falling observer who enters the horizon, it's eventually like going into a mirror copy of our universe. There's no singularity, but there is really a mirror copy. Anyway, please, you don't have to comment on it. Yeah.
Yeah, we have to do calculations and see what happens.
Yeah.
You know, the analytic continuation of the Kerr geometry doesn't happen.
Okay, so more questions, please. So you are hopeful, Andrew, that string theory can be revived and made successful if we agree to give up supersymmetry.
I'm not saying I'm right, but I think this is a path that people could consider. And if it leads somewhere, that would be delightful.
Sure. Thank you. So should we wind up, please? So we still have 15 minutes of our usual time slot, but we could close early. And thanks so much, Andrew, for giving us new insights. I just want to check if there's another comment. Yeah. So we will wind up. We'll meet up on November 15th at David Jackson's talk, which is also about unification, right, David?
Yes, yes, that's right. It's a new approach to unification. That's right.
You could give us a 1 minute abstract of what you will be talking, just to make us curious.
Yeah, so if you think of extraspatial dimensions, it's kind of starts out by thinking about that, but then putting the focus more on proper time than dimensions of space, if you like. It's a bigger generalization at the local level from extraspatial dimensions. There's kind of an assumption that the form of proper time should be quadratic to get a kind of a spatial element in there. But if you're adding matter, that doesn't need to be quadratic, if you like. So you can add on some, say, cubic or quartic term to proper time. And that connects with groups like E6 and E7, which are good for unification and so on. So I'll talk a bit about that, and then I'll talk about the quantum gravity.
So these are not extra time-like dimensions.
No, not at all. No, in fact, there are no extra space or time dimensions essentially. It's more of a generalization of
your picture is quite different from string theory then.
Oh yes, completely different from string theory. Yes. Yeah, that's right.
But
yeah,
you do have exceptional groups like E6, E7.
That's right. It comes in from the exceptional Jordan algebra, H30, the octonions, and the Freudian triple system for the E7. It's like there's a cubic and a quartic form with E6 and E7 symmetries that the Lorentz group kind of embeds in.
Okay, great. Thank you for the introduction. So the cat is bothering you, is it?
Yeah, that's right. Yes, sorry. It just made me jumped on the table here. Yeah. Thanks. Yeah.
All right. So maybe request you all to please leave first, because I don't want to leave before you. Once you have logged out, I will close the meeting. Bye-bye. Thank you, Andrew.
Thanks.
Thank you very much for a great talk.
And
Bye.
goodbye.